This map is the reason the modern economy exists. We think Greenland looks massive because of a mistake, but that's not quite right. It's actually a feature that took 2 centuries to perfect, designed to save shipping companies money for the last 300 years. The Mercator projection, the map you probably grew up with in school, makes Greenland appear roughly the same size as Africa. In reality, Africa is 14 times larger. But here's what nobody tells you about this distortion. It wasn't designed for geography teachers or curious students. It was designed in 1569 by a Flemish cartographer named Gerardus Mercator, but it took 150 years and a series of mathematical breakthroughs before anyone could actually use it the way Mercator intended. European trade in the 1560s had a problem. Ships carrying gold from the Americas, spices from the East Indies, and textiles from Asia needed to cross thousands of miles of open ocean. The captains navigating these routes used compasses, which always point north. On a globe, if you follow a compass bearing, you trace a curve called a rhumb line. That curve is difficult to plot, difficult to follow, and difficult to teach to sailors who might not read well. Mercator had a vision for solving this with mathematics. He created a projection where any straight line drawn on the map would represent a constant compass bearing. A captain could plot a course from Lisbon to Havana with a ruler and a protractor, then hand that bearing to his helmsman. Follow that single number, and theoretically, you arrive at your destination. No complex calculations mid-voyage. No consulting astronomical tables in a storm. But there was a catch. Mercator didn't explain how to actually construct his projection. He published the map in 1569 showing the final result, but the mathematical instructions were missing. Mapmakers couldn't replicate it accurately. Sailors couldn't use it reliably. The brilliant idea sat mostly unused for 30 years. The breakthrough came in 1599 from an English mathematician named Edward Wright. Wright published a book called Certain Errors in Navigation that finally explained the mathematics behind Mercator's projection. He didn't just provide a formula. He laboriously calculated tables showing exactly how far apart to space the latitude lines on a Mercator map, computing values for every single minute of arc from 0 to 75 degrees. With Wright's tables, mapmakers could finally construct accurate Mercator charts. But even then, practical navigation faced 2 massive obstacles. First, determining longitude at sea was nearly impossible without accurate clocks. Second, magnetic declination, the difference between magnetic north and true north, varied wildly across the ocean and nobody had mapped it. These weren't small problems. A navigator using a Mercator chart could be 2 or 3 compass points off course, potentially hundreds of miles from where they thought they were. Wright himself acknowledged this limitation in his book. The map was theoretically perfect, but the technology to use it properly didn't exist yet. So for most of the 1600s, Mercator charts remained specialized tools used by a handful of mathematically sophisticated navigators. The Dutch East India Company, established in 1602, primarily relied on older chart styles. Portuguese and Spanish fleets continued using their own cartographic traditions. The revolutionary projection existed, but the revolution was waiting for technology to catch up. Now, if you want to understand the economic engines that really drove history, the inventions and systems that shaped everything from colonial trade to modern shipping, subscribe to this channel, because we often look at the past through battles and treaties, but sometimes the biggest changes came from someone solving a math problem that wouldn't matter for another century. The technology finally arrived in the 1700s. John Harrison's marine chronometer, perfected in the 1760s, allowed ships to determine longitude accurately for the first time. Edmund Halley created detailed maps of magnetics declination across the Atlantic in the early 1700s, published in 1701. Suddenly, all the pieces were in place. Mercator's projection, Wright's mathematics, accurate timekeeping, and magnetic charts all worked together. Only then, in the middle of the 18th century, did the Mercator projection become the standard for maritime navigation. British navigators adopted it enthusiastically. French merchant fleets followed. By the late 1700s, nearly every major naval power was printing charts based on Mercator's projection with rights corrections. The economic impact was immediate and enormous. Shipping times became more predictable. Routes could be optimized. Training new navigators became faster because the mathematics were standardized. What had taken Mercator's generation years to learn could now be taught in months. Consider the scale of 18th century trade. British ships alone made thousands of voyages to India, the Caribbean, and North America each year. If Mercator charts could reduce each voyage by even a few days, the cumulative savings across the entire fleet were staggering. Time at sea meant wages, provisions, and risk. Faster navigation meant more profit. The Atlantic slave trade, one of history's darkest chapters, also relied on this efficiency. Between 1700 and 1800, roughly 6 million Africans were forcibly transported across the Atlantic. Mercator charts helped slave ships maintain their courses, making the horrific journeys more predictable and therefore more profitable for the traders. The mathematical precision that Mercator and Wright developed had become infrastructure for atrocity. Spanish silver fleets continued their routes from the Americas well into the 1700s. Mercator charts helped them navigate the Caribbean's complex currents and avoid pirate-infested waters. The Dutch, French, and British East India companies all standardized on Mercator for their spice trade routes. By 1750, the projection had become the universal language of maritime commerce. But something strange happened as Mercator charts became ubiquitous. The maps began appearing in contexts that had nothing to do with navigation. Publishers started using Mercator for general world atlases. Educators adopted it for teaching geography. A tool optimized for sailing ships became the default way people visualized the entire planet. This migration from ships to schools accelerated in the 1800s. As public education expanded across Europe and North America, Mercator maps covered classroom walls. Children learned geography from a projection designed for 18th century merchant vessels. The distortion that made economic sense for naval navigation became visual doctrine for everyone else. Greenland's massive appearance on these maps wasn't random. Mercator's projection stretches everything near the poles to keep compass lines straight. At 70 degrees north latitude, where most of Greenland sits, the distortion is extreme. But in the 1700s, when the projection became standard, nobody cared about Greenland. The island held no strategic ports, no valuable trade goods, and minimal population. What mattered was the trade routes. The Caribbean, with its sugar plantations, India with its textiles and spices, the Spice Islands of Indonesia, West Africa's slave trade ports. On Mercator charts, these regions appeared relatively accurate because they're near the equator. Greenland's distortion was simply the price of keeping those profitable routes easy to navigate. By the 1800s, the economic justification had been forgotten. Publishers kept using Mercator because it was familiar, because the printing plates already existed, because changing would cost money. Educational institutions used it because that's what the publishers printed. Generations of students internalized a world where northern regions looked vastly larger than they actually were. The first serious challenge came in 1855 from a Scottish clergyman named James Gall. He proposed an equal area projection that maintained accurate landmass sizes. The projection showed Africa at its true enormous size and shrank Greenland to its actual modest dimensions. But it gained almost no traction. The British Empire, at the height of its power, had no reason to change. The Royal Navy had been using Mercator for navigation for over a century. Officers trained on it. Charts were printed for it, and it worked perfectly well for its intended purpose. The distortion only mattered if you cared about visual accuracy, and the people making decisions about maps, shipping companies, and naval departments did not. More than a century later, in 1973, German filmmaker Arno Peters independently reinvented Gall's projection. Peters presented it as a political corrective, arguing that Mercator's distortions reinforce colonial attitudes by making European and North American nations appear larger than equatorial countries. He called it the Peters projection, apparently unaware that Gall had created an identical design in 1855. The controversy revealed how deeply the economic logic of the 1700s had embedded itself in global culture. Professional cartographers largely dismissed Peters. They pointed out that while it preserved area, it severely distorted shapes, making countries appear unnaturally stretched or compressed. They also noted somewhat acidly that Peters had simply rediscovered Gall's work and claimed credit for it. But activists and educators embraced the Peters projection. Development organizations started using it in their materials. The debate became less about cartography and more about politics. What had started as a navigation tool optimized for 18th century commerce had become a symbol of colonial power structures. What got lost in the argument was the original economic purpose. Mercator created his projection to solve a practical problem for sailors. Wright made it mathematically usable in 1599, but technology wasn't ready, so it sat dormant for over a century. Only in the 1700s, when chronometers and magnetic charts caught up, did the projection finally serve its intended purpose, making ocean navigation more efficient and profitable. The distortion was never an accident. It was the deliberate consequence of prioritizing navigation efficiency over geographic accuracy. The merchants and naval powers who commissioned charts in the 1700s needed the Caribbean to be reachable, the spice routes to be navigable, and the silver fleets to arrive on schedule. They got exactly what they paid for. Greenland's inflation was simply overhead. Modern shipping still uses Mercator-derived charts, though now they're digital. GPS and satellite systems have made straight-line compass navigation less critical, but the conventions persist. A captain plotting a course across the Pacific still sees a map where distances and shapes are distorted, but compass bearings are simple. The economic logic that justified the distortion in the 1700s still applies when time is money and fuel costs matter. Meanwhile, Greenland remains visually massive in popular consciousness. The island's actual area is about 2.16 million square kilometers. Africa measures 30.37 million square kilometers, making it 14 times larger. On a Mercator map, Greenland can appear almost as large, depending on the specific variation used. This isn't a bug in the system, it's the system working exactly as designed by 18th century economic priorities. The map was optimized for profit and efficiency, not visual truth. The distortion was acceptable because the people making decisions, the merchants, naval officers, and colonial administrators, didn't need Greenland to look accurate. The broader lesson extends beyond cartography. Economic incentives shape our tools, and those tools shape how we see the world. Mercator optimized for the needs of 18th century maritime commerce. The distortion was a feature, not a flaw, serving the economic engines that built colonial empires and global trade networks. Consider what else in our modern world follows this pattern. Financial markets use simplified models that distort reality to make transactions efficient. Algorithms optimize for engagement over accuracy. Infrastructure prioritizes speed over other values. In each case, we've traded one form of truth for another form of efficiency, and the distortions become invisible over time. The Mercator projection is just the oldest and most literal example. For nearly 5 centuries, we've looked at a map designed to move cargo faster and assumed it showed the world as it is. Greenland looks big because making it look accurate would have offered no benefit to the 18th century merchants and naval powers who finally made the projection practical. The visual lie was economically irrelevant to the customers who mattered. They cared about reaching India, not about Greenland's visual accuracy. They cared about Caribbean sugar, not about polar distortion. The map gave them what they needed, and we inherited what was left over. Today, cartographers have developed dozens of projections with different trade-offs. The Robinson projection balances distortion more evenly. The Winkel Tripel minimizes overall error. The orthograph attempts to preserve both area and shape, but Mercator persists, especially online and in navigation. The final irony is that Greenland itself has become economically significant in ways that 18th century navigators never anticipated. Climate change is opening Arctic shipping routes that could reduce voyage times between Europe and Asia by thousands of miles. Greenland's mineral resources, including rare earth elements critical for technology, are increasingly accessible and valuable. The island that was economically irrelevant when the Mercator projection finally became practical now sits at the intersection of shipping, resources, and geopolitics. And it still looks enormous on the maps we use every day. That's the real story of why Greenland looks big. Not because cartographers made a mistake in 1569, but because 18th century merchants and naval powers made a choice when the technology finally existed to use Mercator's vision. They chose speed over accuracy, profit over proportion, efficiency over visual truth. The map shows us exactly what they valued. We just forgot to ask what they were willing to ignore to get it. So here's the question to think about. What other tools are we using today that were optimized for someone else's economic priorities decades or centuries ago? What distortions have become so familiar we don't even see them anymore? If you want to keep exploring the economic systems that shaped history and continue shaping our present, subscribe, because understanding why the map looks wrong and how long it took to become useful might help us see what else we've been getting wrong all along.